Okay, so page 271, we're going to start talking about the derivative as a rate of change. So this is the mean value theorem and Rolle's theorem that we're going to be talking about. So let's just go ahead and get started and we'll take a look at the new ideas. So consider the values of a differentiable function f of x in the table below to answer the questions that follow. Plot the points and connect them on the grid. So take some time. All of these points that are listed here, let's go ahead and plot them on our grid and connect them. After you connect them, you should get something that looks like this. So we're going to use the information from our table and our graph that we just created to answer some of the questions and ideas that we go over on the bottom of the page. Alright, so in calculus, the derivative has many interpretations. One of the most important interpretations is that the derivative represents a rate of change of a function. When speaking of rate of change, there are two rates of change that can be found that are associated with a function: the average rate of change and the instantaneous rate of change. So what's important that we're talking about right now is the rate of change of a function. That's what's going to be important in this unit. And the average rate of change, this means between 2 points. Between 2 points, the average rate of change. The instantaneous rate of change is at 1 point. At 1 point. Alright, so let's talk about this average rate of change then. So the average rate of change of f of x on an interval. So we're specifically talking about an interval. So kind of like a definition first before we look at the above. On the interval, bracket a, b, so some given interval. They're going to give you an interval to talk about in the problem. So on the given interval, the average rate of change is f of b minus f of a divided by b minus a. That'll be our average rate of change. So that's 2 points. We're finding f of b, that's one of our points. F of a is another point. And then we're going to subtract the values of those points we chose on the bottom. So that's finding the average between 2 points. That's the average rate of change. The other one we're going to have is the instantaneous rate of change. This one's at a point. So the first one's an interval. The second one is at a point. So at a value, x equals a, the instantaneous rate of change is f prime of a, so the first derivative at that point, which I think we should be familiar with that. We found the derivative, we've evaluated a derivative at a specific point, but what that actually is, that's that instantaneous rate of change, or that slope, at that specific point. So in other words, this is slope of tangent. If this is the slope of the tangent, yeah. If that's the slope of the tangent, do we know what it's called if it connects at two places, if we have 2 points? Slope of what? A line that connects at 2 points.
Slope of secant.
Yes, this over here is the slope of secant. Very good. So this is the slope of the secant, this is the slope of the tangent. Alright, so we're going to use these definitions to apply them to the bottom 2 problems, and these bottom 2 problems are referring to that graph that we drew up above. So we want to find the average rate of change of f of x on the interval 2, 12. So they have given us an interval, and we know its average rate of change, so we have to use 2 points. So if we use the formula f of b, that would be the 12, so f of 12 minus f of 2 divided by b minus a. Well, b is 12, a is 2. 12 minus 2. Okay, well now we actually need to go up above to find what our values are. So at 12, you can either look at your graph or at your table from up above. You have both. If you apply the function at 12, what is our answer? Use your chart or the graph, it doesn't matter. F of 12 is what? 8, very good. Minus f of 2, well f of 2 is what? 5. And then we have 12 minus 2, that's 10 on the bottom. So our average rate of change is what? 3 over 10. So that's the average rate of change, or the slope of the secant, between 2 and 12. So if we go ahead up here at our points, that'd be 2, 5. So that's this point right here. And 12, 8, which is this point right here. And I'll try a different color. We'll see if we can see it. Some of these markers aren't working well. Yeah, that one's not working. Okay, so we have that secant line there. We know the slope of that secant line we found was 3 over 10 down below. So this is the secant line. Secant line whose slope is equal to the average rate of change. And then you could list on the interval from 2 to 12. So that's the secant line whose slope is equal to the average rate of change on the interval 2 to 12. Alright, so that was from this first problem at the bottom. We know that the average rate of change was 3 over 10, and we represented that on the graph up above. So let's take a look at the instantaneous rate of change. Is the instantaneous rate of change of f at x equals 4 greater than the rate of change at x equals 6? Justify your answer. So let's go up to the graph. So at x equals 4, so at x equals 4, we would be right here. We would have a tangent line that goes right there at x equals 4. They also want us to look at x equals 6, which would be right here. So I would have a tangent line at x equals 6 like that. So I have those two tangent lines. One at x equals 4, one at x equals 6. From looking at our two tangent lines, what can we justify? Which one is greater? Which one has a greater rate of change? Yeah, and how do you know it's greater? Yeah, it's steeper, exactly. So f prime of 4 is greater than f prime of 6 because the tangent line at x equals 4 is steeper. Very good. The derivative at 4 is greater than the derivative at 6 because the tangent line at x equals 4 is steeper. Very good. Any questions so far about the difference between the average and the instantaneous? One's with 2 points, the other is with 1 point. Ariana, were you able to catch up?
Yeah.
I don't want to flip it before you're ready. So just let me know if you're ready to turn over. We are going to go to the back side, so if you want to flip your page or get ready for the back side. All right, thank you. All right, so on to the back. We're going to start with what is called Rolle's theorem. So we're going to lay it out, and then we'll see how we can actually use it with a few examples. So Rolle's theorem. This states if f of x is continuous on the interval bracket a comma b, differentiable on parentheses a comma b, and f of a equals f of b, then there is a guaranteed to exist value of C on AB. Or there's guaranteed to exist a value. Sorry. Then there is guaranteed to exist a value of C on that interval AB such that f prime of C equals 0. So I know it's a lot to take in at first, but let's get it written down, then we'll take a look at it, what it actually means. So if f of x is continuous on brackets a to b, if it's differentiable on a to b, and if you evaluate a and evaluate b, they're equal to each other, then there is guaranteed to exist a value of C somewhere on that interval in between a and b, such that the derivative at that point is equal to 0. Does anybody think they know what that means exactly, or can it describe it? You think so? Go ahead. Okay, so how can you guarantee that there is a max or min there? How do you know that's happening according to this Rolle's theorem? Not sure? Alright, so if we let's draw a little picture, or I'm just going to draw one. You don't have to necessarily draw it if you don't want to. I'm going to draw it here. Now this is not the answer for this question, so don't copy it down in the box, but I'm just going to draw a picture. So if I evaluate and I pick 2 points, A and B. So I have some coordinate plane, and I pick some value of A over here. And that value of A is equal to whatever this point would be here on my graph. So I evaluated it, it's right here. Stating in Rolle's theorem, f of b, whatever value b may be, so I'm going to say b is over here. I pick b, well b has to be the same value as a. It states in the theorem f of a has to be equal to f of b, so they're the same y value. It said it has to be continuous, so we know from a to b we have to be connected the whole way. There can't be any gaps or anything. We know it has to be differentiable, so we know we can't have any sharp points. If it is, we're guaranteed to exist some value c where the derivative is 0. So that means if I have a graph maybe that comes down like this and comes back up and ends there, because we're only looking at that interval, do I have a spot where the derivative is 0? Yes, down here. where it changed signs there. So I'm going to try to erase this as best I can. Okay. Let's say maybe this function goes up here somewhere and then comes back down. Do I have somewhere where the derivative is equal to 0? Yeah, right there. So that kind of talked about the min and max that was mentioned earlier. What if I have a function that for some reason just goes straight across? Do I have some point C in the middle where the derivative is 0?
Yes.
Yes, I do. The derivative is just where you are horizontal. If I take the derivative at any point in this example, the derivative is 0 the whole way across there because the slope is what? 0. So what they're saying, as long as you know your endpoints are at the same value and it's continuous between them and there's no sharp points, any way you draw any sort of line or curve to connect the two, there's always going to be some point where you can get the derivative equal to 0. Does that make a little more sense with the picture now? No matter how you connect them, as long as you're continuous and no sharp points, it's differentiable. It says it has to be differentiable. There's some value C in the middle where the derivative will be 0. Okay? So that's what this theorem is stating. So now that we know kind of what the theorem is stating, let's try to put it into practice. Consider the function f of x presented on the previous page. Does Rolle's theorem apply on the following intervals? Explain why or why not. So I know I accidentally already erased the front, but you still have it on your page if you want to flip. Look at the interval from 2 to 14. From your x values of 2 to 14. Is it continuous? Okay. Is it differentiable? Can you take the derivative at any point from 2 to 14? Okay. Is f of a, so f of 2, and f of 14, are they equal to the same value? Yes, they are. So now we're saying that there's guaranteed somewhere between there to exist some value c that the derivative of that point is 0. Okay? Is there a point, if you look between that interval, where the derivative would be equal to 0 from 2 to 14? Yeah, there is. So let's make a statement here then. Rolle's theorem is applicable for f of x on 2 to 14 because f of x is continuous, and you should say that it's continuous on the interval, differentiable on the interval. So we're going to say is continuous on 2 to 14, differentiable on 2 to 14. Again, continuous, you want the brackets. Differentiable, it's the parentheses, 2 to 14. And f of 2 is equal to f of 14. And if you look at your chart or your graph, the value of that was what? It was 5, so they were equal to each other. They were both 5. So the guaranteed value of C is what? So we said it's continuous, it's differentiable, the endpoints are equal to each other. So somewhere in between A and B, again remember, 2 is A, 14 is B if you want to label that over here. A and B. Somewhere between A and B, there's some point C where the derivative is 0. That's what we're looking for. So what is that value of C? What is the value of C between A and B where the derivative would be equal to 0? It is 8. Very good. So at the x value of 8. So C is 8. At that point, that's where the derivative would be equal to 0. Alright, let's go ahead and look at the next one then. So the interval, again, you can refer to the front, but we're looking at the interval from 2 to 8. So A to B. From 2 to 8, is it continuous? Okay. Is it differentiable? Can you take the derivative anywhere from 2 to 8? Yes. Is f of 2 and f of 8 equal to each other? No. Okay, so we can say although f of x is continuous and differentiable, Rolle's theorem doesn't guarantee a value of c and I'm going to have to write down here just to finish it. Guarantee a value of c such that f prime of c equal to 0, because f of 2 is not equal to f of 8. So although f of x is continuous and differentiable, Rolle's theorem doesn't guarantee a value of c such that the derivative at that point is 0, because the endpoints are not equal to each other. Could there occur a spot where the derivative was equal to 0 between those? Is it possible? Yeah, it's possible, but according to the theorem, it's not guaranteed. We don't know for sure. If all of these stipulations are true, we know for sure there's a guarantee that there will be, but we don't know for sure. It's possible, yes, but not guaranteed. So that's what we're stating with the theorem. Any questions how we applied the theorem to either of those problems? So we had one where it worked, one where it did not work. Does anybody need anything repeated? We're okay with those ideas so far? Alright, because of the shortened periods, we're going to stop there. We'll leave these for tomorrow. That way we don't get stopped in the middle of a problem, okay? So if you want to start maybe looking at homework to see what the homework problems would look like, you could do that. Otherwise, we are done for today.